Welcome to Brain Vision.
So here we try to find the maximum force of the lever arm. So we can say that this system has rotational equilibrium as well as translational equilibrium. So we can take the sum of torque around point C. This is going to equal 0, and this is going to equal T sine of theta times H minus F times H times over 2. So tension is going to equal the force divided by 2 sine of theta. So we can say that the net torque about point D is also 0. This is going to be equal to force of friction times H minus F of H over 2. Therefore, the force of friction is simply going to be equal to the force divided by 2. So we can say that the sum of forces in the y direction equals 0. This will equal the normal force minus T cosine of theta minus the weight. So we can say that N, the normal force, will be the weight plus the tension cosine of theta. And we can say that the force of friction is going to equal the coefficient of static friction times the normal force. This is just by the definition of the force friction. And this will equal mu S times W plus T cosine of theta. And at this point, we can say that the force of the lever arm over 2 has to be less than or equal to the coefficient of static friction times the weight plus F cosine of theta divided by 2 sine of theta. And so we find that F is going to be less than or equal to 2 times mu sub S times the weight times 1 minus mu sub S cotangent of theta. So this is going to be equal to 2 times 0.3 times 400, and then divided by 1 minus 0.3 times cotangent of 36.9 degrees, and F has to be less than 399.7 newtons. So it has to be less than or equal to 399.7 newtons. This is for the lever arm. And so for part B, we can say that the net torque about point C is going to equal 0 once again. So this will be T sine theta of H minus F times 0.6 H now. So this means that T is going to be equal to 0.6 F divided by sine of theta. So we can say that this net torque about point B is going to equal 0. This will equal the force friction times H minus the force of the lever arm times 0.4 H. And so we can say that the force of friction is simply going to be 0.4 times F. We can take the sum of forces in the y direction. This is going to be 0, and this will again be the normal force minus the tension cosine of theta minus the weight. We know that the normal force is going to be the weight plus the tension cosine of theta. Again, force of friction must be less than or equal to the mu S of N. We can say that force of friction has to be less than or equal to the coefficient of static friction times the weight plus T cosine of theta. And we can say that 0.4 further substitute, so 0.4 F has to be less than or greater than mu S plus T cosine of theta. My apologies for it being cramped. And then we can finally say that 0.4 F has to be less than or equal to mu sub S W plus 0.6 F cotangent of theta. So we can say that F has to be less than or equal to mu sub S times the weight times 0.4 minus 0.6 mu S cotangent of theta. And at this point, we can solve. So this is going to equal 0.3 times 400 newtons, and then divided by 0.40 minus 0.60 times 0.30 times cotangent of 36.9 degrees, and we find that F must be less than or equal to 749 newtons. This will be our final answer for part B. That is the end of the solution. Thank you for watching.